see you there. As you can tell, we're here today at Jay Peak to help teach physics to the Lesu folks.
A vector quantity is described by magnitude with direction. The Lachute is an example of a vector quantity because you drop downward at a speed of 60 miles per hour. Scalar is a quantity described by magnitude. Floating down a lazy river is an example of a scalar quantity because we're traveling at about 5 miles per hour.
Here we are at the lazy river. Olivia and Alyssa are going to demonstrate what distance and displacement are. Distance is how far you have traveled, while displacement is how far you have traveled from your origin. They start here at the beginning of the river and go around the whole thing, which is 750 feet long. The total distance they have traveled is 750 feet, but their displacement is 0 feet because they started and ended at the same place.
The end.
Emily and Hannah have a constant speed, which is a scalar quantity. When they go around the corner, their speed stays the same, but their velocity changes because their direction is changing. Velocity is a vector quantity, and this means that they have accelerated because acceleration is a change in velocity over change in time.
Objects free fall towards the Earth at an acceleration of 9.81 meters per second squared. As the object falls, a pattern occurs in its drop path due to the force of gravity. This pattern is shown by the distance the object gets in each frame. Each frame increases by the previous frame's distance.
Force causes acceleration. In this clip, we see Chad's velocity change by the downward force of gravity, resulting in acceleration. We know that acceleration equals change in velocity over change in time. We also know that velocity is a vector quantity of both magnitude and direction. Though Chad's speed down the trails may stay constant, the force he applies to the ground and snow allows him to change direction, resulting in acceleration.
On land, our weight is 160 pounds and our mass is 72.6 kilograms. Because of this, our weight makes it difficult to pick someone up.
When we're in the water, our weight decreases because of buoyancy. This makes it easier to pick the other person up. Our mass stays the same because the amount of stuff inside us does not change.
Quiet. Hi! I'm gonna talk about equilibrium. I got it here. Right now, I'm in equilibrium. This means simply that the net force acting upon me is 0. This is because my velocity stays the same. Now, if we look... On the moment of impact, he lost his equilibrium. Now he's got it back. But, as you can see, it hurts a little more.
Alright, this is Thomas Meyer, Nathan Legue, explaining to you standard 14, force normal. Gravity right now is from the center of my mass, pulling me straight down. Force normal is going to be exactly perpendicular and opposite that force. So from my center of mass, it's going to be pulling me up the same distance with the same amount of force.
Okay. Newton's first law: an object in motion stays in motion, and an object at rest stays at rest unless acted upon by unbalanced forces.
Newton's second law. Acceleration is directly proportional to force and inversely proportional to mass.
Third law. For every action, there's an opposite and equal reaction.
This is an object in motion. It'll stay in motion until an unbalanced force stops it. This is an object at rest. It will stay at rest until an unbalanced force acts on it and moves it. And then it will stay in motion till friction causes it to stop.
Bennett and I did Standard 19, Newton's second law.
Newton's second law is demonstrated by F equals ma, which means force equals mass times acceleration. To show this in a real-world situation, I skied into Bryce, who was at rest. When I hit him, my force transferred into him, so I stopped, and he accelerated forward.
How about that fall?
Dude, that hurt.
Why was that?
Newton's third law.
Oh yeah?
Yeah, man. Going down the hill, bombing, going out.
That's a lot of force.
It is a lot of force, man. I hit the ground, guess what? The ground hit me back. The same amount of force, and as you can imagine, it didn't feel too good.
Yeah.
Wow. I've learned a lot. How about you, Seth? I have too, Sean.
Water slides are a great way to demonstrate momentum and impulse. Momentum is a mass in motion, so everyone going down the slides has momentum, like shown here. The biggest example of momentum here is the aqua loop.
As someone falls down the chute, they gain momentum, hopefully getting enough to make it around the loop. But just in case they can't, there's a trap door in the slide so they can get out. When the person hits the water at the bottom, that is an impulse, a change in momentum.
How did that feel? It felt fun because it was larger, so it made the force on my feet greater. Lower. Good.
Now, how did that feel?
Didn't feel great because the
time was a lot
smaller, so the force exerted on my feet was greater, so it kind of hurt a little bit.
Okay.
An elastic collision is a collision where kinetic energy is conserved. Colliding objects rebound and move away from each other after the collision. Here's an example.
An inelastic collision is a collision where kinetic energy is not conserved. Colliding objects do not rebound and they possibly stick together. This is what it looks like.
Hey kids, are you tired of these old physics textbooks? Yeah! If yes, then throw this shit out. Then try Physics DVD. What's work? Great question.
When Paxton lifts up the board, work is being done. Work is done when a force causes a displacement of an object. Other examples of work are when the lift does work to pull you up the mountain, and gravity does work to bring you down.
So, the law of conservation of energy states that energy cannot be created or destroyed. This means that one cannot make energy or get rid of it. It simply changes from one form to another. The total energy in the system remains the same as well. That means when I'm standing here on my snowboard at the top of a hill, standing still, I have the same amount of energy as now when I'm whizzing down on the mountain on my snowboard. However, earlier I had potential energy. Now I have kinetic energy. The total amount of energy has stayed the same, but it has changed from one form to another.
So, Anthony, I
at the top of the jump line, and we're going to show you guys the distinction between potential and kinetic energy. And potential is stored energy, and kinetic is energy in motion. And when Anthony yells kinetic, that's when we have more kinetic energy. And when I yell potential, we have more stored energy. So here we go, and this is our max potential. Potential! Kinetic! Kinetic! Potential!
Hello, I'm Robert, and today I will be showing you the difference between linear, tangential, and angular velocities. Derek is cruising in a straight line. Notice how his distance traveled, or displacement, changes over time. This is a constant linear velocity.
In this next clip, notice how Ben and Derek rotate about a single point, the axis. They both complete the same number of rotations in any given amount of time. This is angular velocity. At the same time, notice how much greater the displacement of their right arm is than that of their left arm. This demonstrates tangential velocity.
Before I go off the jump, my linear speed is going to be the speed of my straight line, and gravity is going to be pulling me down the hill, so it'll be a constant acceleration. And angular speed, I'm going to be doing a 360 off a jump and then a 540, and I'm going to have a greater angular speed of the 540 because I'm doing more rotations in the same amount of time, traveling greater distance. And my tangential speed, if I have my arm out, my hand will have a greater tangential speed than my shoulder because it's farther away from the center, or the axis.
Wow, that was phenomenal.